start talking about what makes atoms and elements different from one another, okay? There is one distinct property that makes an element different from another element. One distinct thing. Does anybody know what that is? The number of protons. Number of protons that each atom has is the one distinct characteristic that makes it different than another element. Okay, it makes a very distinct difference. So if an atom has 8 protons, it's always oxygen, no matter what. Doesn't matter how many neutrons or electrons it has. If it has 8 protons, it is oxygen. If it has 7 protons, no longer oxygen. It's now nitrogen, right? If it has 6 protons, no longer nitrogen, it's carbon. Okay, so the protons is like the distinct characteristic that makes an element an element. The number of protons that an element has a nickname. Do we know what that nickname is? It's called atomic number. Very good, atomic number. Okay? Some books abbreviate it with a Z. I don't even really need you to know that because I will never do that. I put it in there because your book does, but I don't love it. But the atomic number is individual for each atom. So for each element. So I want you to look at your periodic table. Pull your periodic table out. The atomic number for each of these elements is listed at the top of the box. Okay, and really in the top corner. Okay, so do you see the top corner of each box? It's got a whole number there. It has to be a whole number because it's just the set number of protons. You can't have a partial proton, right? So the atomic number for phosphorus, which is just P. Can you locate phosphorus?
15.
Its atomic number is what? 15. Okay? What element has the atomic number 26? Iron. Good. Okay, if I'm looking at my periodic table, we need to remember that the periodic table is ordered by increasing atomic number. So here is atomic number 1 with hydrogen, 2, 3, 4, 5, 6, right? It goes in order to the right and then down, right? Do you see how that's organized? Anyone, bonus points for who can name the scientist that organized it by atomic number? No, Mendeleev was atomic mass. Who was atomic number?
He was Russian, right?
No, Mendeleev was Russian. Henry Moseley put it by atomic number. Okay, that's tricky. Okay. But we see this organization that goes by atomic number, so it's really easy to locate. Okay? So for silver here, we see atomic number is 47. The atomic number of an element never changes. It never varies. If I change the number of protons on an element, I've changed the element completely. Okay? So if I start with 47 protons, I have silver. If I add a proton to that, what element do I have now? Look on your periodic table. If I go from 47 protons to 48 protons, now I'm at cadmium. Yeah, cadmium. Okay? All right, so what I want us to think about now is if we're talking about protons, where did we find out protons are located at? In the nucleus. And what charge do protons give off? Positive charges. Okay, so we need to think now about the atomic number and what happens in an atom, okay? If an atom is neutral, what do you think that means its overall charge is? What does neutral mean? It means not positive or negative. Neutral means I've got an overall charge of 0. So if my atom is neutral and I have 10 protons in my atom, how many electrons do I have to have? 10, right? That's it, 10. So the atomic number also tells us the number of electrons in the atom as long as that atom is neutral, right? As long as the atom is neutral, the atomic number tells us both protons and electrons. They can have different numbers of neutrons. Okay, so there can be 2 oxygen atoms that have different masses, that weigh different things. Okay, and these have a special name called isotopes. Okay, I would maybe highlight that, put a little star by it, because we definitely need to know what the definition of an isotope is. Okay, definition of an isotope is atoms of the same element with different masses. Okay, and I'll explain how that works out here in just a second, but I want you to get that definition down real quick. All right, so remind me of what's present in the nucleus of an atom. Protons and neutrons. And what two parts make up the mass of an atom? Protons and neutrons, right? Both located in the nucleus. Do we count in the mass of electrons when we're counting the mass of an atom? No, because what did we say that how much smaller are they than a proton? Do you remember? Like 2,000 times smaller than a proton, right? So the mass is so small and so insignificant, we consider it to be negligible, right? We're going to ignore it. And so when we're talking about isotopes, we're looking at oxygen atoms. Let's use oxygen as an example. An oxygen atom always has 8 protons, okay? You'll see me abbreviate proton with P and a little plus, right? Why do you think I would use P and a plus? It's got a positive charge, right? Okay, so if I've got 8 protons and 8 neutrons, that gives me a mass of 16, right? 8 protons plus 8 neutrons. If I've got an oxygen atom that has 8 protons and only 7 neutrons, that gives me an atomic mass of 15. But are both of those atoms still considered oxygen? Yes. And why is that so? It's all about protons, right? As long as my atom has 8 protons, it's considered oxygen, right? That's really the bottom line. And then any other numbers of neutrons make them now isotopes of one another, okay? Isotopes just mean we're different versions of oxygen atoms. Okay, some atoms have really a one single abundant isotope. That means like 99% of those types of atoms have a weight of 16, for example, and maybe only 0.02% have a weight of 15, right? It's there, but it's not very common. And I'll show you how we kind of pick that out on the periodic table, okay? But here's an example of hydrogen and its isotopes, okay? The most basic isotope of hydrogen is just called H1, and it's just named hydrogen, right? It's got one single proton, no neutrons at all, and 1 electron, okay? Look at your periodic table and look at what's the atomic mass of hydrogen. You see it? 1 point what? 1.008. Okay, so 1, if its atomic mass is 1, that means it's got 1 proton plus 0 neutrons, right? That adds up to 1. We've also got another version of hydrogen called deuterium, and deuterium has 1 proton, which makes it hydrogen, and 1 neutron, which all that affects is its mass. Okay, and then we've got something called tritium, which is H3, or it's hydrogen with 1 proton, because that's what makes it hydrogen, and 2 neutrons. Now, these 2 isotopes, this one and this one, not very common, right? Let's say if I pulled 1,000, let's say if I pulled 100,000 hydrogen atoms, there might be one of this and one of this, right? Might be. I don't know the percentages off the top of my head, but it's a pretty small number, right? There's not very many of these versions of hydrogen, right? Far and away, we see hydrogen look just like this. But there is these stable isotopes that are available, okay? And they occur just not very abundantly, okay? What questions do we have about the concept of isotope? Yeah, Jamie.
Okay, so every single atom is considered an isotope, not just the ones that differ in neutrons.
Right. So let's look at oxygen. Oxygen has an atomic mass of 16, which means, or 15.99. That means oxygen's most abundant isotope has to have a mass of 16, and then it has maybe its second most abundant isotope might be 15, right? It lowers that atomic mass just a little bit. We'll look at that here in a little bit. Okay, so now let's talk a little bit more about atomic mass. We already said that atomic mass is the total number or the sum of protons plus neutrons in the nucleus. Okay, atomic mass is protons plus neutrons. But what I hope you're wondering, I want you to look at your periodic table, and I want you to look at the atomic masses that are listed. Look at the atomic masses that are listed. They're the bottom number, right? For carbon, it's 12.011. Do you see what numbers I'm talking about? Okay, look at all those atomic masses. Do they look like just an easy sum of protons plus neutrons? Do they look like their whole numbers? No. Okay, the reason they are not is because the mass that you see right here on the periodic table is a weighted average of all of the isotopes of that element. Okay, so let's see, for example, oxygen. We'll talk about oxygen again. Oxygen has an atomic mass of 15.999. Okay, so if we're talking about a weighted average of atomic masses, what do you think the most abundant isotope for oxygen would probably weigh? 16, right? It's really, really close to 16. So we might have a most abundant isotope that weighs 16 AMU. And then what do you think our second most abundant isotope might weigh? Right? It could weigh 15, 14. It could be something that's less than 16 AMU. Right? Our number one isotope has to be at 16. Number two isotope is some mass less than 16 because our weighted average got pulled down from 16. Does that kind of make sense how we can see that? So let's look now at aluminum. Aluminum has an atomic number 13 and an atomic mass of 26.982. So what do you think aluminum's most abundant isotope might be? 27, right? And its second most abundant isotope probably has a mass higher than 27 or lower than 27? Lower than 27. You see what I'm talking about there? Our average gets pulled down just slightly, not a lot. So there's not very many of those that weigh less than 27, but there is some that's pulling that number down, okay? What about chlorine? Look at chlorine. Chlorine's atomic number 17. What's chlorine's atomic mass? 35.453. So what is that telling us about the isotopes of chlorine?
It's very.
Yeah, there must be a pretty even split, right? Because if this is a weighted average and this is falling near the middle, 35.5, that means there must be at least two isotopes that are pretty abundant. Right? Maybe 50% of them weigh 35 and maybe 50% of chlorine atoms weigh 34. Right? Do you see how there's a difference there with this weighted average? Because this one falls more in the middle. Okay, so the closer we are to a whole number, that means we've got one isotope that's super abundant. And the closer we are to, the middle of two numbers or closer to 0.5 means we've got a spread out of abundance of our isotopes. Okay? The atomic number always tells us the number of protons for sure, and it tells us the number of electrons, but what's the caveat with the number of electrons? Bingo. We got to have it in a neutral atom. Okay? So atomic number always tells us the number of protons that are present. It tells us the number of electrons, but it's in a neutral atom only. Okay? How many protons and electrons are in a neutral calcium atom? How many protons and electrons are in a neutral calcium atom? Calcium is in group 2. Raise your hand once you think you know. Calcium's in group 2 if you're still looking for it. Tell me how many protons and electrons are found in a neutral calcium atom. Not yet. Raise your hand. All right, Evan, what do you think? What'd you say? 20 split evenly, like 10 and 10? 20 of each. 20 protons and 20 electrons. I would agree. Okay, this is how I'll abbreviate electrons. E with a little minus. Why would I use E with a minus? Negative charge. Good. Okay, so I know it's 20 because atomic number is 20. That tells me protons. And if it's neutral, I know protons have to equal electrons. Okay? If I want to find the number of neutrons, I've got to focus on the atomic mass of an atom because I know the atomic mass is number of protons plus the number of neutrons. So what would I do if I wanted to solve for the number of neutrons in an atom? What could I do? Bingo. All I have to do is subtract. Okay, I've got that written out here, but you can write it in your own words if you want. But if I want to find the number of neutrons, I take atomic mass minus atomic number, and that would give me the number of neutrons that I need, right? Atomic mass minus atomic number. It works for either, because the neutral part of it, the charge part of it, is really only affected by an electron change. The neutrons don't affect charge at all, so it doesn't matter what the charge is for neutrons. Good question. Okay, when we're trying to find neutrons too, you will round the mass, the atomic mass, you'll round it to the nearest whole number. Okay, either I will give you the isotope mass we're focusing on, or you'll round it to the whole number if I don't. Okay, so let's look at an example here, uranium-235. When it's written like this, that tells me I'm looking at uranium isotope with a mass of 235. Right, that's what I'm looking at. Uranium with a mass of 235. So I want protons, neutrons, and electrons in uranium-235. Protons, neutrons, and electrons. Okay, so can we locate uranium yet? Uranium is just a U. It's in the actinide series, if that jogs anyone's memory. Okay. Can we locate it yet? What's its atomic number? 92. So what's that tell me about protons? 92. And also about electrons? 92. Okay. We will know if an atom is neutral or not based on if it has a charge listed. So it would have if it has a charge, it'll be listed up here, almost like an exponent. Okay, it's called a superscript. If it had a charge, it would be listed up there like that. -2 or +1 or whatever. Okay, but with nothing there, we assume it's neutral. So now if I want to find my neutron number, I take 235 minus 92. 235 minus 92 gives me 143 neutrons. Seems simple enough? Okay, in this case, I was given my atomic mass or the isotope I was focusing on. If I was not given that, I would round mine to a whole number. Okay, so you'll notice uranium on your periodic table is 238. We use the isotope that weighs 235. Okay, so it's got 3 less neutrons than the one that has on our periodic table. Okay, or the weighted average. All right. Questions about neutral atoms. All right, we're going to switch gears here and talk about atoms that are not neutral. Okay. So what happens if we have a different number of electrons than protons? What happens if that number is not the same? It becomes a charged atom, right? Our atom now takes on a charge. Does anyone know what that is called? There's a certain name for charged atoms. Starts with an I. An ion. Good. Ions are any atoms that have charges. Okay? So an ion is any atom that has a positive or a negative charge. Any atom that has a positive or negative charge. When we're dealing with things that have charges, I want you to think about this real quick. If I want to change the charge of my atom, would I add a proton or would I change my electron numbers? Electron numbers. So here's the things. Because if I change my proton, what happens? I change the element, which is a problem, right? I change the element. So if I need to change the charge of my atom, it deals with electron changes, not with proton changes. Okay? So what would happen if I have more electrons than protons? What type of charge would that lead me to? More electrons than protons. What do we think? A negative charge. This is counterintuitive because when I add electrons, that makes me think I want to be positive, right? But an electron has a negative charge. So if I'm adding electrons, I'm compounding the negative, right? I'm making a negative charge. So more electrons than protons is a negative charge. Okay, and these have a special name called anions. Anions. Okay, so any atom that has a negative charge is considered an anion. Okay, anyone that has a negative charge considered an anion. And like I kind of pointed out before, if it has a charge, it will be written up similar to like an exponent. Okay, up on the top right. So O, -2. I don't know, chlorine, -1. Whatever it might be, phosphide, -3, right? Those are all charged atoms, and we see a negative written in front of it like that. You'll see some books even write the charges as 3-. Not my favorite, but it gets done that way, okay? So that means the same thing. As anytime it's got a negative, it's still that anion, okay? So now what happens if I have less electrons than protons? What type of a charge? It's a positive charge, right? More protons. 9 protons, 8 electrons leaves me with a charge of what? If I have 9 protons and 8 electrons, what's my charge?
1.
+1, right? So these are called positive charge, and they have a name called cations. Cations. How many of you people are cat people? Because I'm not a cat person, is that cations have a plus sign right in the word. Okay, cations have a plus sign right there. So we know that cations are the positive version. Okay, very good. Yeah. If I had lithium that has 1 less electron than its protons. So think about lithium. How many protons does lithium have?
3.
Lithium has 3 protons. And let's say I have 1 less electron. So that would mean 3 protons and 2 electrons. What would my result be here?
+1.
Okay? It would be lithium with a +1 charge. Okay, so here's what I'll tell you. If it's a 1, sometimes you'll see them leave that number off. So it might just be listed as lithium plus. Okay? If there's no other number there, we assume it's a 1. Sometimes you'll see it written, but sometimes you won't. I just want you to know that. Positive or negative, if it's a 1, it can be left off. Okay, so if it was chlorine minus like that, we know the charge is -1. Okay, +1. Very good. What happens now if I have oxygen with 2 more electrons than protons? It leaves me with a negative charge, and a negative charge of what?
2.
O -2. Okay, how do we feel about that? O -2. So I'm going to ask you to be able to identify protons, neutrons, and electrons in both neutral atoms and in ions, right? You're going to have to do both of those things. Okay, let's try a couple more of those. Let's tell me the protons, neutrons, and electrons in phosphide. So P -3. I want to know protons, neutrons, and electrons in that atom. Okay, let's try that real quick. And then we'll move on to our very last thing for today. Protons, neutrons, electrons in that. What type of ion is this?
Positive. Negative.
So what's it called? No. Cations are positive. It's an anion. All right, good. What did we have for protons? Bowden, what'd you have? Yes, good. Is the number of protons affected by the charge? No. Phosphorus always has 15 no matter what. What about the electrons? 18. Very good. Sometimes it's easy to think -3, we subtract 3. That's not how it works, right? -3 means I have 3 extra electrons. Are we good with that? Okay, and then what about neutrons? 16. Good. Atomic mass, 30.97, so we round up to 31. We take 31 minus 15. That gives us 16. Okay, are we good with that? We talked about how isotopes occur as different versions of the same type of element. And we talked a little bit about, we talked a little bit about how the mass you see on the periodic table is a weighted average of the isotopes. Okay, so now we're going to see how that mass is calculated. I talked about it's a weighted average. So the average atomic mass that you see on the periodic table, this is not the atomic mass of a single isotope. It's an average of all of the isotopes. Okay, so the average atomic mass takes into account how much of each isotope is in an average sample. You don't necessarily have to write down all this intro stuff here, but I do want you to have the equation down that we're going to see, okay? So the mass that you see here is a weighted average of all of the isotopes of that element, okay? You don't know the percentages based on just looking at this, but you can tell which one is the most abundant, okay? So here's the equation that I want you to write down. AAM just means average atomic mass. Average atomic mass. And what you do in this equation is you take the percentage of isotope A times the mass of whatever that isotope is. Then you add that to the percentage of isotope B for that element times its mass. You add that to however many isotopes you have, right? If you've got 6 isotopes, you'll do that 6 times and add them all together, okay? But we'll see an example here pretty soon. I want you to make a little note here with these percentages. The percentages need to be decimals. So if it says it's 89% of this isotope, that would be 0.89 times the mass, right? We have to convert that percentage to a decimal before we can put it into our equation, okay? So let's look at an example here. I've got an example that's 69.17%. 69.17% with a mass of 63. And another isotope that is 30.83% with a mass of 65. Okay, so I've got 2 isotopes here. If I pulled out 100 of those molecules, 69 of them would have a mass of 63, and 31 of them would have a mass of 65. Does that make sense how that works? Right? If I pulled 100 of these unknown atoms, that's what would happen. Okay, so now let's figure out how to put this into the equation. Okay, I take the percentage of isotope A times its mass. So the percentage I convert to a decimal, 0.6917 times the mass, 63, plus the percentage of isotope B times its mass, 0.3083 times 65. Okay, go ahead and grab your calculator out if you don't have it out just yet. Right? Shouldn't my answer come out to be between 63 and 65 somewhere? And don't you think it should be a little closer to which one? Should probably be a little closer to this because it has a higher percentage. So that means when I did the math, I got 63.62. We can leave it there. AMU. That would be the average that would go on the periodic table for that particular element. Go ahead and try this one by yourself, and then that'll be the last one we do, okay? This has 3 isotopes. One that's 87% abundant, one that is 10% abundant, and one that is 3% abundant. So you're going to need 3 terms in your equation. We want to make sure we have to do what to those decimals? We want to make them, I'm sorry, I think I said decimal. We want to put them into a decimal. So you got to divide by 100. Okay? But I got 33.25. Okay, what does AMU stand for? atomic mass unit. That's the unit that goes with it. Okay, so that's saying we've got so many protons, so many neutrons added up. And that's what so this is the number we would see on the periodic table for this particular unknown element, right? It's the weighted average. So that's how those numbers came about and how those numbers are decimals, not whole numbers.